This video will combine the three distinct styles we have seen in previous videos. First, where we draw dynamically on a tablet. Second, a more static presentation of a fixed PDF file. And third, the real-time evaluation of a MATLAB M file. Okay, so we're going to begin with a PDF file. We're dealing here with 2x2 systems of first-order ordinary differential equations. And this video is actually the first in a series of three dealing with such equations, such systems. In this video, I'll concentrate on linear systems. Nonlinear systems will be treated in the next two videos. So here's our basic setup. We have a system of two differential equations. X prime, or dx dt, is an expression in tx and y, and similarly dy dt is another expression in tx and y. The assumption is that tx and y range each over some interval, perhaps an infinite length, and both f and g are nice continuous functions which have continuous first partials with respect to the x and y variables. And under those hypotheses, we actually have an analog of our basic existence and uniqueness theorem. It says what you would expect given any fixed point t0 in the interval of definition for t, and two initial values, x of t0 is x0 and y of t0 is y0. Of course, x0 and y0 are in the respective intervals of definition. Then there is a unique pair of functions, a single pair, xt, yt, defined on some interval containing t0, and that pair satisfy both the system of equations and the initial data. Okay, that said, we now specialize to autonomous systems. So an autonomous system is one in which neither f nor g depends on t. So the t is gone up here. And so we can rewrite as x prime equal fxy, y prime equal gxy. And we can also write that in a vector shorthand in the usual way. Okay, so now before I specialize to linear systems, where the little f and little g are linear functions, I want to mention three topics that will be important in what follows. Critical points, phase portraits, and vector fields. So let's start with critical points. The set of points in the plane in which f is 0 is of course just a curve in the plane. And similarly, the set of zeros of g is another curve. And as I say here, under very mild conditions on f and g, which are met in all the circumstances we encounter, the intersection of two curves like that is a discrete set of points in the plane. Those points are called the critical points of the system. If x0, y0 is a critical point, then it should be absolutely obvious that if we define the parametric curve given by the parametric equations, x of t is x0 for all t, y of t is y0 for all t, so that curve is nothing more than a point. In fact, that's a solution to the system because both sides will be 0. Since the x and y are constant functions, the derivatives are 0, and f and g are by hypothesis 0 at the critical point. And so for that reason, critical points are sometimes called equilibrium points. The system is in equilibrium there. It doesn't evolve over time. If it starts there, it stays there. Later, when we study nonlinear systems, we shall develop methods for determining the nature of solutions near to critical points, and we'll see that sometimes this gives us valuable information about the long-term behavior of solution curves. Okay, that's A. Now B, phase portraits. So it's useful to view a solution pair, xy, xt, yt, to an autonomous system as parametric equations for a curve in the xy plane. The collection of all such curves corresponding to all initial data is called the phase portrait of the system. Of course, if we can find formulas for x of t and y and t, then it is straightforward to draw the curves and to see the phase portrait. Often, especially for nonlinear systems, it is impossible to find symbolic or formula solutions to a system, so we have to work graphically or numerically to generate an approximate solution. The graphical approximation is called a vector field. I'll give examples momentarily. And as I said, for nonlinear systems, generally we have to draw a phase portrait using numerical approximations. But for linear systems, we can actually solve the equations and use those solutions to draw a phase portrait. In a moment, I'll invoke MATLAB to draw some sample phase portraits for the various cases that arise for a linear system, cases that you'd I think know by now arise by examining the different types of eigenvalues for the coefficient matrix. But first, let's do a little work by hand. Okay, so we're studying a system x prime equal fxy, y prime equals gxy. And the first thing we want to note is that the level curves, so those are the points where f is 0, and the other level curve is where g is 0, that those level curves in the plane typically look something like this. So let's suppose that we have one curve like that, and let's suppose this is g equals 0. And we have another curve maybe looks something like this. This is f equals 0. They intersect in 2 points, and those are our critical points. And let's assume, let's say that on this side g is positive, and down here g is negative. And similarly for f, let's assume that f is positive to the right and negative to the left. And then we observe the following, that in the neighborhood of each of the 2 equilibrium points, there are 4 regions or quadrants, and in those, what determines the direction of the solution curves is the following. X is increasing where f is positive, and of course it's decreasing where f is negative. Similar for y is increasing when g is positive and decreasing when g is negative. So in the 4 regions around each of those points, we look at where the solution curves are increasing and decreasing, and we draw little arrows to indicate that. So for example, over here, I'll do something like this. So that's supposed to suggest that both f and g are positive there, the x is increasing, and the y is decreasing. Whereas up here, f is still positive, but g is now negative, so we get a set of arrows like this. And we do that as we go around, and so this is what you get. And down in here, we get that y is increasing, but x is decreasing. And similarly, down by the lower point, of course over here we're going to get the same thing. But things change. Over here the arrows look like this, and down here the arrows look like that. And finally over here f is negative and g is also negative, and so the arrows look like that. So that's a rather primitive diagram, but you're supposed to be able to deduce the nature of the solution curves from those arrows. And so if you stare hard enough, you maybe think that the solution curves are doing something like this, and something like, whoops, sorry, like that over here. And so this point is what in the terminology of the course is called a saddle point. You have curves sort of bypassing it. Whereas over here, what looks like is going on is you've got things going around. So it's either a spiral point or maybe a circular point, where the curves are closed curves going around there. So those are speculations based on this rather primitive drawing of a vector field, but of course MATLAB can do far better, and so that's what we want to turn to next. Continuing, the primitive vector fields that I just drew by hand can be improved dramatically if instead we employ MATLAB. The code for doing so is supplied in the Differential Equations with MATLAB book, and let's look at a few representative examples. The first of the 3 below is linear. This one is clearly linear. The other 2 are not. This one is not linear, and example 3 is not linear. Okay, so let's now invoke MATLAB to get these done. Okay, I'm going to have MATLAB solve the three problems and draw the vector fields for the three I just outlined. As usual, it's good to clear everything. These of the three, the first one will be linear and the remaining two nonlinear, and we use the template from the differential equations with MATLAB book from the 15th chapter. So here's our first example, obviously linear. And here's the code that generates the vector field. So we'll use mesh grid and quiver. There's your linear system right there. I'll let you read the various options in the MATLAB book. Let's see what comes out. So there's the result. This is obviously a case where the origin is a spiral point. Okay. Now, and that's what it said there. It looks like all the solution curves are spiraling clockwise into the origin. Here's the second example. Again, just copied from the previous screen. If you look carefully, you'll see that the level curves are hyperbolas. X minus 2 plus the square root of 1 plus y squared equals 0 is basically x minus 2 squared minus y squared equal 1. Second one is also a hyperbola. The orientations are different. And in fact, well, I'll jump down to below. This example yields level curves exactly like the ones that I drew in the previous screen. So let's see what comes out. Same template. The only thing that changes here is the system. Let's run it. And we get more or less what was predicted. Right? Remember, there were 2 points. The upper point was a saddle point, and that's clearly the case here, saddle point. And the lower one was a spiral point, and the curves were all spiraling away from that critical point. And so, actually, the primitive diagram wasn't so bad. It actually gave us a good indication of what the solution curves were near the critical points. So that's all it says here. The vector field confirms the upper critical point's a saddle point, lower one's a node from which the solution curves are spiraling out in a counterclockwise direction. Finally, just a second. Okay, I'm resuming. There was a slight error in the code there, which I fixed. So there it is. It's the same example that was the third example on the other screen. Again, the MATLAB code is the same. The only thing that changes is the system. Let's see what we get. Wow, that's interesting, huh? So this is a very interesting dynamical system. It has 4 equilibrium points. 1 here, 1 there, and 2 down here. This one is clearly a saddle point. Let's blow this up a little. Right, so there's the saddle point. This guy's a spiral point, and down here we have nodes. This one is an asymptotically stable node. All the solution curves are coming in, and this one is an unstable node. All the solution curves are going out. So as I say here, I won't take the time, but you can verify that there are 4 critical points, and I've given you their coordinates. And from the vector field, you get the nature of the critical points exactly as I just said. All right, the final chore now is to draw the phase portraits for a linear system. So there's a linear system, or as I say, written out in coordinates. X prime is ax plus by, y prime is cx plus dy. Before I do that, there's a point I should have perhaps made earlier, a point which is obvious from the pictures we've been drawing and from the words I've been saying, namely that for an autonomous system, linear or nonlinear, the solution curves don't intersect. The phase portrait is a bunch of solution curves that fill up the region of definition with no intersection. And that follows rather easily from the existence and uniqueness theorem, and hopefully your instructor has shown you that little argument in class. So let's go on. You did also learn in class that the portraits for a linear system vary depending upon the eigenvalues of the matrix A. Those eigenvalues were computed in the notes and in class under the assumption that A was non-singular. And I'm going to draw representative portraits for each of the cases for the different eigenvalue possibilities. But we can also dispose of the case where A is actually singular. Your instructor may not have done that. So in that case, the null space of A, that is the set of X for which AX equals 0, is not empty, and it doesn't consist just of 0. It's either 1 or 2-dimensional. So if it's 2-dimensional, that says that every vector is killed by A. That is, A is just a 0 matrix, in which case every point is a critical point, and the phase portrait is the rather uninteresting portrait consisting of all the points in the plane. Every point is a solution curve. So that's not so interesting. Let's look, on the other hand, at the case where the dimension of the null space is 1. That says that A has to have 0 as an eigenvector, but there are still two possibilities. Either there is another non-zero eigenvector for A, or there isn't, but the eigenspace of 0 is still only one-dimensional. So let's look at those two cases. What happens? In the first case, then there are two linearly independent vectors, xc and eta, which satisfy these two equations. The first equation says that xc is an eigenvector corresponding to the eigenvalue 0. And the second says that eta is an eigenvector corresponding to the other non-zero eigenvalue. So lambda is the other non-zero eigenvalue. So in this case, basically you have the two eigenvalues, 0 and lambda, and it's very easy to write down the general solution. It's given by this expression, a constant times the eigenvector 0 times e to the 0t, of course e to the 0t is 1, plus another constant times e to the lambda t times the eigenvector eta corresponding to lambda. So these are all the solution curves for that case. And now let's draw the phase portrait. Okay, continuing, so here is our general solution. X of t is c1 xc plus c2 e to the lambda t eta. So what do those solution curves look like? Here's our axes, and let's, for the sake of argument, assume that xc looks something like this, and eta perhaps is up here like that. And what kind of curves do we get? Well, first let's consider c2 equals 0, c1 not 0. Then, since there's no t, we just get a set of points along that line. Right? So every point on that line corresponds to a solution curve. Right? That corresponds to c1, xc, and c2 is 0. Now what happens when c2 is not 0? So then we take a point here, c1, xc, and add to it c2 e to the lambda t, and t varies from minus infinity to infinity, and so we're going to get a line parallel to eta, actually like that. And let's assume that lambda is positive. Then we're going to get that line. Right? Okay. On the other hand, if C2 is negative, then we're going to get the half line going this way. And so we'll get those lines off all these points. Right? What happens if lambda is negative? If lambda is negative, we get the same curves, but the direction of motion would be in the opposite direction. Okay, and so what we get is a series of points along a line. Points along a line. That's all these points. And then we get a series of half lines, all parallel, coming off that line. Okay? And the direction of motion is determined by the sign of the eigenvalue lambda. And now the second case, in that case there are eigenvectors xc and eta which satisfy these two equations. C is an eigenvector corresponding to the eigenvalue 0. There is no other eigenvector, but since the eigenspace is one-dimensional, there must be a second linearly independent vector satisfying an equation like this. Okay. This time the general solution is given as follows. So this is the method that sort of corresponds to reduction of order. If you haven't seen this, I'll let you check that this is a second solution. So these are the general solution. And now what does the phase portrait look like? Okay, now the second case, the general solution is x of t is equal to c1 xc plus c2 times t xc plus eta. And what kind of a picture do we get this time? So again, let's take xc here and eta here. And once again, if we start with c2 equals 0, we get all the points along the eigenvector xc. So every point on this line is the solution curve. But now what happens when c2 is not 0? What we're really doing is we're doing c1 plus c2t c plus c2 eta. So we adding a constant times eta, so let's say a point like here, say if c2 is less than 1, and then we add c1 plus c2t along xc, where t can be any number, so we're basically just going to get a line parallel to xc, and the direction of motion will be positive. If c2 is positive, if c2 is negative, then we're going to be down here, and the lines are going to go in the other direction. So again, we get points along a line, and we get a bunch of parallel lines, but they don't come off of xc, they're parallel to xc. So the lines are parallel to the eigenvector corresponding to 0. So there's the two pictures that perhaps you didn't see. They're not in the notes. But that's what happens in the two cases that you have a singular matrix. Finally, let's consider the situation in which the 0 vector is the only vector in the null space of A, and that means the origin is the only critical point. And as we know, the various phase portraits that arise are completely dependent on the nature of the eigenvalues of A. Now, none of which can be 0. The 5 cases to be examined are these. The first, 2 distinct real eigenvalues of opposite sign, 2 distinct real eigenvalues of the same sign, 1 repeated non-zero real eigenvalue, 2 complex conjugate eigenvalues with non-zero real part, and 2 complex conjugate purely imaginary eigenvalues. Okay, here are 5 representative systems, one for each of the cases 1 through 5, and their phase portraits, as drawn by MATLAB, using the symbolic solution of the linear system in each case, which MATLAB can compute. Okay, here we go. Autonomous linear systems, sample vector fields. Let's clear everything. I take the code from chapter 14 of the MATLAB book, and I'm going to run through these rather quickly. There are 5 cases. I've picked sample equations in each case. They're all linear. This is the case where we have 2 distinct real eigenvalues of opposite sign. I'll let you on your own look at the code, but it's essentially copied from chapter 14. Let's evaluate and see what kind of vector field we get. What kind of phase portrait. There it is. That's the one that corresponds to a saddle point when we have 2 real eigenvalues of opposite sign. Bigger so you can see it. Okay, next case is 2 distinct real eigenvalues of the same sign. Here's a sample case. Let's evaluate. And there we go. You can see the two eigenvectors here and here, and incidentally you can also see them in the first case. There's your two eigenvectors. So you can see the eigenvectors in both cases. The other ones were the saddle curves. This is sort of the half U-shaped curve. Let's run to the next case. One repeated real eigenvalue. That's where you have these kind of hook-shaped solution curves. Let's see. Here they are. And there's only one eigenvector this time. There's the solution curves. A little hard to see the hooks. Two more left. This is the case with two complex conjugate eigenvalues with non-zero real part. We should see spirals. Let's see. There they are. And finally, the fifth case, purely imaginary eigenvalues. We should see circles or perhaps ellipses, as we do see here. As I say, the elliptical curves are evident. Well, that completes our look at linear autonomous systems. In the next two videos, we'll examine nonlinear autonomous systems.